Welcome to The Explainer. Today, we're digging into the invisible forces that literally build everything around us, from the world of nature to some of our most futuristic technology. Okay, so let's start with a puzzle. Picture this, a giant sequoia. It can be over 80 meters tall. That's basically a 30-story building. Yet somehow it gets water from its roots all the way up to its highest leaves, completely defying gravity. How on earth does it do that? All right. Here's another one for you. The Boeing 787 Dreamliner. It's a total marvel of engineering. And a big reason why is that it's made of these advanced materials that make it way lighter and more efficient than older planes. So what's its secret? Now, the amazing thing is, the secret behind both of these marvels is exactly the same, and it all happens at a scale that is completely invisible to us. It comes down to the subtle, tiny attractions between individual molecules. Okay. Let's dive in. So to solve those puzzles, we have to zoom way, way down to the molecular level. And it turns out there's one really crucial idea we need to get straight. The difference between the forces within a single molecule and the forces between separate molecules. On one side, you have intramolecular forces. These are the big guns, the super strong bonds that hold a molecule together. You can think of them like the steel frame of a skyscraper. Incredibly powerful, defining the whole structure. But then, on the other side, you've got intermolecular forces. These are much, much weaker attractions between different molecules. So if the first force is a steel frame, this one is more like a bunch of weak magnets trying to hold two finished buildings close to each other. They're not nearly as strong, but they're what determines how all those individual molecules act as a group. And here's the thing. These weak forces have their own power rankings. There's a clear hierarchy of strength, from the very weakest London dispersion forces all the way up to the superstar of the group, the hydrogen bond. This little hierarchy is basically the master controller for how substances behave. It dictates if something is a gas, a liquid, or a solid, and it's the key to pretty much everything we're talking about today. So at the very bottom of that ladder, you've got London dispersion forces. Even in a perfectly balanced molecule, the electrons are always whizzing around. For just a split second, they might bunch up on one side. This creates a tiny temporary charge. And that fleeting charge can then cause a ripple effect in a neighboring molecule, creating a very weak, very short-lived attraction. It's not much, but it happens in every single molecule. But let's just jump right to the top of that hierarchy, to the most powerful of these weak forces. Because this one force explains some truly bizarre and totally essential properties of a substance we all rely on every single day. Water. A hydrogen bond is like a dipole-dipole force on steroids. It happens when hydrogen is bonded to a really electron-greedy atom, like oxygen. The oxygen pulls the electrons in so close that it leaves the hydrogen with this little bit of positive charge sticking out. And that positive bit is then super attracted to the negative end of a neighboring molecule. The result? It's like molecular Velcro. It makes water molecules incredibly sticky. And this is where you can really see the power of those hydrogen bonds. Just based on its size and what we know about other similar molecules, water should boil at a freezing cold, minus 100 degrees Celsius. But we all know it boils at 100 degrees. That huge 200-degree gap you see on the chart, that's the raw power of hydrogen bonds. It's all the extra energy we have to pump into the water just to pry those sticky molecules apart from each other. And this isn't just a quirky fact for chemistry class. These bonds are absolutely fundamental to life. They are the very force that holds the two strands of your DNA's double helix together. They give proteins the complex folded shapes they need to work as tiny machines inside our cells. Without them, life as we know it just wouldn't be possible. Okay, so we have all these different forces, some strong, some weak. It's the way they all play together that dictates how molecules lock themselves into place to form the solids that make up our world. So how does that actually work? Well, when molecules lock into a nice repeating pattern, they form what's called a crystalline solid. And almost all of them fall into one of these four main categories. The big takeaway here is that the type of connection, whether it's a strong bond or just a weak force, directly determines the final properties of the material, everything from how hard it is to what temperature it melts at. Let's look at carbon. It is the perfect example of how structure is everything. You arrange carbon atoms in this rigid 3D lattice where every single atom is strongly bonded to four others. What do you get? You get a diamond. That interlocking network makes it incredibly strong, the hardest natural substance we know of. But take those exact same carbon atoms and instead arrange them in flat sheets. Now, within each sheet, the bonds are still very strong, but between the sheets, all you have are those weak little London dispersion forces. This means the layers can slide past each other really easily. The result is graphite, the soft, slippery stuff in your pencil. Same atom, completely different structure, and a completely different world of properties. Metals are a whole different story. The electron C model is a great way to picture what's going on. You can imagine the positive metal atoms are like fixed islands, just sitting there, in a shared sea of electrons that are free to move anywhere they want. Because those electrons can move so freely, they can easily carry an electric current. This sea also lets the atoms slide past one another without breaking apart, which is why you can hammer a metal into a new shape.
Okay, so now that we have this framework of forces and structures in mind, let's circle all the way back and finally solve the puzzles we started with.
So that giant sequoia, how does it drink? It's all about hydrogen bonds. Inside the tree's trunk, there are these incredibly tiny tubes. The water molecules, thanks to their stickiness, stick to each other. That's cohesion. And they also stick to the walls of the tubes. That's adhesion. Together, these two forces create what's called capillary action. It's a chain reaction where water molecules literally pull each other up the tube, one after another, defying gravity all the way to the top.
And what about the Dreamliner? Its secret is composite materials. Engineers weave these incredibly strong carbon fibers, which get their strength from that same kind of covalent network we saw in diamond, and they embed them into a lightweight plastic. The result is a brand new material that's both unbelievably strong and incredibly light. And this isn't just a minor detail. More than half of the Dreamliner's entire structure is made from these advanced materials. That's a fundamental revolution in how we build airplanes. And it's all possible because we've learned how to master the bonding structures of solids right down at the atomic level. So in the end, whether you're looking at the surface tension that makes a water droplet beat up or the silicon chip that's powering the device you're watching this on, the story is the same. These unseen forces, the strong bonds holding molecules together and the weaker attractions between them, are the silent architects of our entire physical world. Which of course leaves us with one final big question. We've mastered these forces enough to build superplanes and to understand the code of life itself, but we're really just getting started. As we get better and better at arranging atoms and controlling these forces, what new materials and technologies are we going to build next?